Now, I want to continue on lecture 9, talking about nanocomposites. Many of these nanocomposites are polymer-based nanocomposites. There are probably ceramic-based nanocomposites or metal-based nanocomposites, but they are very few, and not all of them are really suitable to be extruded or formed into shapes using additive manufacturing processes. But even among polymer based nanocomposites, there is a limitation that uh, these cannot easily be formed into shapes because there is a limitation to the amount of filler that can be nano filler that can be added. And it is also pretty well known that this limitation happens mainly due to agglomeration of those nanoparticles and due to the low surface energy of those particles, so they don't really bond well with the matrix. um, I was part of a group from Rice University that looked at the effect of additive manufacturing on nanoparticle reinforcement. And just 5% addition of single wall nanotubes. SWNT is single wall nanotubes, and MWNT is multi wall nanotubes. So, those are two different types of nanotubes, and this was done in the, I would say, in the early to mid 2000s. Um, and we found that just adding 5%, but adding 5% is a lot, but adding 5% improved the tensile modulus by 93% and tensile strength by 31%. So you can see that um, adding so much of nanotubes and introducing so much complexity in the processing doesn't really improve the properties a whole lot. But just adding 5% vapor grown carbon fibers improve the tensile modulus by 44% and tensile strength by approximately 27%. So we found that vapor grown carbon fibers, which are cheap, much cheaper than single wall nanotubes, and they are not as complicated to process compared to the nanotubes, did give us something comparable. Not as good, but pretty comparable. So this shows you a bar chart um, of the different materials. ABS is acrylonitrile butadiene styrene, which is a standard thermoplastic polymer, engineering thermoplastic polymer that is used a lot in Stratasys type of equipments. So if it is unfilled, these are the properties, and this is tensile strength, and just 5 to 8% single wall nanotubes using the extrusion freeform fabrication improved it by 31%, the tensile strength. But the modulus increased by 93%. So, as I said to you, it is not that significant when compared to the vapor grown carbon fibers. Now, you can also see that on the fracture surface itself, you can see these small fibers sticking out in these nanocomposites. I believe this is vapor grown carbon fibers because this doesn't look like the nanotubes themselves. But you can see the alignment in the direction of the extrusion. So, what did we find? We found that additive manufacturing process can still achieve preferred fiber orientation even when the fibers are pretty nano-sized. And there is clear evidence of a fiber alignment after the additive manufacturing, and but the nozzle size has to be pretty small. It can only be 50 to 100 times that of the diameter of the fillers. And so what happens is that when you have such a small nozzle, any amount of clogging or the fibers um, going crosswise, which could be very easily possible, can easily clog uh, the nozzle and jack up the uh, the force required to extrude the material through that nozzle. So this is the reason why the standard fuse deposition modeling is not capable of extruding polymer blends with high solids loading. 50% by volume if it is uh, just particles, and fiber loading which is greater than 30% by weight. So it's really not possible using the standard fuse deposition modeling or even the extrusion freeform fabrication. Um, for continuous fiber reinforced process composites, there are only two known processes so far, but no commercially available process. First one is from UDRI, where Dan Klosterman, Dick Chardoff, and Ray Milunas from Northrop Grumman. And Ray Milunas doesn't work at Northrop Grumman anymore. He is at Navair, Pax River. They did something based on laminated object manufacturing, and the basic problem is that none of those AM processes are capable of accurately machining the fiber edges, so you can't really cut them off that easily. And if you use lasers, it can easily damage the fiber mechanical properties. Um, the main problem is that it is difficult or impossible for additive manufacturing to take into account the geometrical issues such as fiber orientation, fiber continuity. So this group demonstrated that it was possible to modify the laminated object manufacturing. So what is laminated object manufacturing? So you take one layer, cut the edges off, lay it down um, on a table, and then go and cut yet another piece and put it on top. So depending upon the XY planes, it can easily do that. And you can also change um, the fiber orientation slightly, but not a whole lot. And what should be noted is that this process was done in the early to mid 2000s, when the additive manufacturing processes were still in their infancy and the software and hardware capabilities were still being resolved. But unfortunately, nobody has really taken the effort to take this forward. Now, there is automated toe placement that can be done, but still, that is a difficult process. So this is the schematic of that laminated object manufacturing process that they did. I'm not going to go too much into detail about that. You can read through this and figure out, what is done here. And what it is you have a heating lamp array. It heats up and um, kind of lays it down on top of the previous layer. Um, this is the actual equipment itself. Now, this was a equipment that they put together. They had an existing laminated object manufacturing machine that they modified to fit this process, because there was no technique or machine that could do additive manufacturing of continuous fiber reinforced composites. Uh, so this was a modified laminated object manufacturing. And this is a simple component that was fabricated by laminated object manufacturing. So there is some slight curvature and dips and overhangs and things like that, but not a whole lot. Okay, so um, I was part of a group that did yet another process where we looked at ceramic composite automated toe placement, or we called it CCATP. So this is based on automated toe placement, which is the standard polymer composite technique. So based on thermoset prepregs being placed down and laminated, or you could wind it around a mantle and things like that. So here the automated toe placement employs two hot gas nitrogen torches, and the first torch and roller is to preheat the composite surface and the incoming toe together, and the by doing that the layer is tacked to the surface. So you could use a pre-preg tape rather than a whole fabric. So you could do that, and you could change the direction of the fiber. And we had to figure out a way to cut and refeed the mechanism. So, and the main heater provides a supplemental through thickness heating and bonding of the toe and substrate under the consolidation roller. And these rollers will provide the necessary forces, and once it is done, it can be cut with some kind of a um, cutting mechanism. So this is a standard repeating pattern or with brick face symmetry. So this is the toe placement machine, and this is a schematic uh, of the process itself. So you have two rollers, and these are some of the processing conditions for carbon pre-preg toes, and we modified that for ceramic composite toes. So in that case, we had to make some modifications. So we had the original preheater torch is set to operate at 500 degrees centigrade. So we disabled one of those rollers because we didn't want this um, thermoplastic binder to be melting and flowing all over the place. And we also reduced the gas flow rate of the preheated torch to reduce the heating conditions. So this is the close-up view of the rollers, two rollers. So one of the rollers is a preheating roller, the other one is the tamping down roller. We were also able to do this for making ceramic bladed discs. But the unfortunate part is that the cutting is not really efficient. So we did do something. So we had to simulate the tool path, and that told us what exactly we had to do. Um, but it still wasn't the best process. So this was done in the early 2000s. Um, Seems like a long time ago. Anyway, so these were some of the products that was made by the ceramic composite automated toe placement process. So we were able to make some cylinders, but again, because of the amount of matrix and the fibers and the difference in the thermal expansion coefficient between the matrix and the fibers, we didn't always get a crack-free component. So we talked about the in situ fiber reinforcement already. So I won't go into too much into depth. So you can look into that. And we looked at um, polyethyl oxazolene with a polystyrene polymer. So both of them, when we extruded them and heated them up, you got in situ fiber reinforcement, which really increased the strength of this fibrous material. So this was the process that we used for, actually this was the material that we used as a water soluble support material for extrusion freeform fabrication. Okay, so here is one thing I want to tell you about papers for your term papers. If you are looking at these papers only on the presentation itself, you won't be able to double click on this. But if you are doing it in display mode, you will be able to double click, and there are papers all the way from 1992 here, and all those papers are free. I don't know how they did that, but it looks like it is free. So you can go and look up these papers, and you can use them as the source for your term papers. And please also look at the Journal of Rapid Prototyping, and there could be other sources also. You will be able to do that. So please look into that and get them uh, get them to use them for your term paper. Okay, and as I said to you, I gave you some suggested methods for your term paper. Okay, Please look into that. Some of you have asked me questions. I don't want to go over them over and over again, but please look into that suggested format of your term paper. I had given that in some of the earlier lectures. Please look into that, and you should be able to get a pretty good idea of what I'm looking for. Okay. Um, anyway, um, this is where I stop, and this is the end of lecture 9.